Alcohol and water do mix is an episode of the Degrees of Freedom Project videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. For most purposes, solids and liquids are treated as incompressible, meaning the density is not a function of pressure. They are also regarded as having a low coefficient of thermal expansion, so variations of density with temperature are often ignored. However, it's not always safe to do so. For example, designing a liquid thermometer is impossible without a knowledge of how the density changes with temperature. From thermodynamics, we have the volume expansivity, which is how the volume of a liquid or solid changes with temperature. It is given by 1 over the volume times the partial derivative of the volume with respect to temperature at constant pressure. The variation of volume with pressure is the isothermal compressibility. It is given by the negative of 1 over the volume times the partial derivative of volume with respect to pressure at constant temperature. For most liquids and solids, beta and kappa are constant, or nearly constant. Values for the volume expansivity and the isothermal compressibility come from experimental data, websites, handbooks, and tables, and equations of state. A web search will often offer lots of leads. In some of the later, more advanced videos, we will discuss the volume expansivity and the isothermal compressibility in some detail, as well as partial molar volume, which is a method for calculating molar volumes for liquid mixtures. For calculating the densities of mixtures of liquids and/or solids, the following principles apply. For ideal mixtures, which is where the attraction between like molecules is essentially the same as between unlike molecules, the density of a mixture can be calculated with volume additivity. The specific volume of the mixture is equal to the sum of the mass fractions of each species times its specific volume. Since the specific volume is the reciprocal of mass density, the formula can be written as the reciprocal of the density of the mixture is the sum of the mass fractions of each species divided by its density. Applying the formula to a binary mixture yields 1 over rho mix equals x1 over rho 1 plus 1 minus x1 over rho 2, or rho mix equals rho 1 times rho 2 divided by 1 minus x1 times rho 1 plus x1 times rho 2. Mixtures of aliphatic hydrocarbons are often close to ideal, so feel free to use this formula when mixing up a batch of petroleum jelly or paraffin wax. If you have to estimate the density of a mixture and you really have no better options, you can calculate the density as the sum of the individual densities times their mass fractions. It really would be nice if the true values for mixtures were bracketed by volume additivity and density average. In material science, the properties of a composite almost always lie between the weighted sum of the individual properties and the reciprocal of the weighted sum of the reciprocal of the properties. But especially with liquids, the values can be way outside these two formulas. We will examine the case of ethanol and water on the next slide to see how bad these formulas can be. Experimental data, handbooks and tables, and equations of state are always your best bet if you can find them. Here's a graph of the density of an ethanol-water mixture at 20 degrees Celsius as a function of the ethanol weight fraction. The volume additivity, calculated with the binary formula, is the orange slightly convex curve and is the lowest of the three curves. The density average, calculated with the binary formula, is the gray or slightly greenish-gray straight line between the two endpoints. The experimental data are the blue concave curve that is separated from the density average by more than the difference between the two other curves. Alcohol and water really like each other and get as close as they can to each other, so the density of a mixture is much higher than you would anticipate. Again, if at all possible, you want a reliable experimental data set or equation of state. The takeaways are 1. Websites, handbooks, tables, and equations of state are the best sources for the density of liquid or solid mixtures. 2. If the mixture is ideal, volume additivity should be fairly accurate. 3. Lacking any other option, density average will at least give you a number. 4. The densities of mixtures of ethanol and water lie way outside both volume additivity and density average. Thanks for watching! This video was brought to you by the DOFPro team.